welcome back. In this lecture, we do one numerical example on mutual information. In previous classes, you have studied much about what is information rate, what is average information, and what is the meaning of information rate. Subsequently, you also know what is mutual information. Mutual information is defined as the amount of information transferred over the channel when symbol ij is transmitted and yk is received. And this is the mathematical expression for mutual information. It is given as P of xi upon yj log base 2 of P of xi upon yj by P of yj. By directly observing the expression, you can see mutual information depends on joint probability, conditional probability, particularly. Okay, and this one is a particular B of xi. Okay. Or you can also write same mutual information in another way also. I of y semicolon x equal to another way of writing the same mutual information equal to sigma I equal to 1 to n, sigma j equal to 1 to n, P of xi yj. The portion is no change, and here it can be taken as P of yj upon xi by P of yj. These are the two definitions for mutual information. However, from the properties of mutual information, we know that is I of x semicolon y anyway is equal to I of y semicolon x, which means that mutual information is symmetric. Okay, coming to our current context, what is the objective? We want to estimate the mutual information for a given conditional probability matrix. Mutual information is characterized by a channel matrix. We know what is channel matrix. Channel matrix is meant for defining the or describing the characteristic of channel. Whether channel is lossy or lossless, that can be easily determined from the knowledge about channel matrix. So, channel matrix is also called as conditional probability matrix or channel transition matrix. Number of names are there. This channel matrix is given in this manner. Okay, so in the rows indicates input symbols and the columns indicate output symbols. In such a case, the channel matrix is generally given as P of y1 upon x1 and P of y1 upon x2. Similarly, P of y2 upon x1 and P of y2 upon x2. This is the definition of channel matrix. We know what is channel. A channel is the medium through which information propagates from transmitter to receiver. Behavior of a channel is a must in describing the performance of a communication system. Now, what is the current task? We want to estimate I of x semicolon y. It is preferable to not go directly to estimate the mutual information by using definition. You can better use this notation, that is properties h of y minus h of y upon x. From the properties of mutual information, we know it is given as h of y minus h of y upon x or h of x minus h of x upon y. Either of these properties can be used for estimating mutual information based on the given data. In the current example, what is given we have been given P of y upon x. It is given as P of y upon x equal to 0.6, 0.4, 0.4, 0.6. Such a channel is called as a symmetric channel. In the problem itself, it has been mentioned. It is a binary symmetric channel. Binary means two input channels, two input symbols, two output symbols. Why symmetry? If you have observed this value or these values are equal and these values are equal. That is why such channels are called as binary symmetric channels. But if you have seen the expression to estimate the mutual information, we need to estimate h of y. What is h of y? H of y is the entropy at the destination side, which can be written as, see this, h of y equals to sigma k equal to 1 to n pk log base to 1 by pk. Or in specific, I can write the same as k equal to 1 to 2 p of yk or yj log base 2 of 1 by p of yj. Better I use the notation of yj only to follow the earlier terminology, okay? Because j corresponds to symbols on the other side. So I use this also as j only instead of k, right? Better. So sigma j equal to 1 to 2. This is j again. Okay. Sigma j equal to 1 to 2. Why 2? Because there exist only two symbols. No, being the channel is a binary channel, we have only two input symbols and two output symbols. So 1 to j. But probability of yj are not given. P of y1 and P of y2 are not given. Then how to estimate them? Either the source symbol probabilities P of x1, P of x2, or the destination symbol probabilities P of y1 and P of y2 can be estimated from the joint probability. Because from the basics of your probability theorem, probability fundamentals, we know one theorem called as total probability theorem. According to total probability theorem mentioned in, we know, which is given as P of A equal to, okay, P of A equals to sigma n equals to 1 to m P of A upon Bn into P of Bn. When there exist capital N mutually exclusive events Bn, and let another event capital A is defined in this sample space or in this on these events, then P of A is given as P of A equals to sigma n equals to 1 to m P of A upon Bn P of Bn. What is m? How many number of events B1, B2, B3 exist? This is known from the total probability theorem. Okay, we know fundamentally there are three theorems no, for probability: multiplication theorem, Bayes theorem, total probability theorem. Now we know what is the definition of joint probability. What I do? I replace this simply. So I replace P of A can be written as sigma n equals to 1 to m P of A Bn, right? This is definition of your joint probability using conditional probability. So what can be written currently? What is required for you? P of yj, right? So P of yj can be obtained from I equal to 1 to m, that is 2 here, P of xi comma yj. For any fixed value of j, the probability can be estimated by adding all P of x1 y1, P of x2 y1, P of x3 y1. Similarly, so on, so on. So in such scenario, first what is required? we need to estimate the joint probability. So let's write the expression for conditional probability, and then we continue how to estimate joint probability. Okay, so given data corresponds to P of Yj, P of Yj upon xi. P of yj upon xi is given, no, that is your channel matrix. So I replace this with P of yj, which is given as P of yj upon xi equal to definition of conditional probability xi yj by P of xi. So what it means, you can be able to get P of xi yj equal to P of yj upon xi into P of xi, right? So I just modify this expression. This can be written as further P of xi, that is probability of input symbols, into P of yj upon xi. So if I just substitute the values given in the problem, what values are given? The probabilities of the values are, I'm writing them in a diagonal matrix. P of x1 0 0, P of x2 followed by your given matrix. What is given matrix? P of y1 upon x1, P of y2 upon x1. Similarly, P of y1 upon x2, P of y2 upon x2, right? Okay. Why we have considered this diagonal matrix is to perform the multiplication property. This gives you 0.250, 0.75. They are the input probabilities, followed by 0.6, 0.4, and again 0.4 and 0.6. They are the conditional probabilities P of y upon x. Upon multiplying all these values, you can get your joint probability matrix as, this will be equal to, first one 0.25 into this is 0.3, and correspondingly this is 0.1, and this is 0.75 into 0.4. The value of this will be equal to joint probability matrix. If you multiply, this is again 0.3, and this will be around 0.6. If you multiply, the values will be 0.45. The value of this is 0.5. Now I know the joint probability matrix. This is your joint probability matrix. P of xi yj equal to 0.3, 0.1, 0.3, 0.45. The value of this is to be replaced. And the first value, let me just mention, this value is not 0.3 actually, it is 0.15. This one also, right? This is 0.15. I need to correct it. Sorry for this small correction. 0.15, 0.15. Let me verify once please. 0.25 into 0.6. Yes, it is 0.15. Right. Now let us continue further. What is our interest? We want to estimate P of yj. So how to get P of yj? This is your P of yj. Y1 can be given as P of y1 equal to 0.45, P of y2, probability of symbol 2, equal to 0.55. So what we got? We have estimated the probabilities of the symbols y1 and y2. Now what is required for you? Okay, I want to estimate h of y, right? This is equals to sigma j equals to 1 to 2 p of yj log base 2 1 by p of yj. Correspondingly, we substitute the values thereof 0.45 log base 2 1 by 0.45 plus 0.55 log base 2 1 by 0.55. So the value of entropy h of y can be if you estimate properly, it will be equals to 0.9925 bits per symbol. This is the average information contained by the symbols y1 and y2, right? Second, first parameter is estimated. Then what is required further? We need to calculate h of y upon x also. Conditional probability has been given. What is the expression for conditional entropy is here mentioned. J equals to 1 to n p of xi yj log base 2 1 by p of yj upon xi. So we know all these values, right? All these values are given, are estimated. Okay. So with this knowledge, let me just mention what are the values given. P of y upon x is 0.6, 0.4, 0.4, 0.6 being symmetric, right? Then P of xi yj already calculated. P of xi yj equal to 0.15, 0.1, 0.3, 0.45. This is the joint probability matrix. So by substituting these in the earlier expression for the conditional entropy, your conditional entropy can be given as h of y upon x equal to, the value will be around 0.97. We need to verify after substitution 0.97 bits per symbol. Units for entropy are bits per symbol. Finally, the mutual information I of x semicolon y equals to 0.9925 minus 0.97. This is equals to 0.02 bits per second. This is your mutual information for the given problem. The key point to mention here is which expression we need to follow is very important. Should we go by definition of mutual information, or should I use I of x semicolon y equals to h of y minus h of y upon x, or should we use h of x minus h of x upon y? It all depends on the data given. In this manner, based on the channel matrix given, you can estimate the mutual information. That is for this class. We continue in the next class. Thank you all.